All right, marvelous humans, we are back in action. Last class saw the introduction of the awesome and powerful U-Substitution method to help us take antiderivatives of what were previously tricky integrals. Today is actually a very short video, I know, gasp, and we're going to focus on antiderivatives of inverse trig functions. Now, I actually used to skip this lesson a few years back, but there's been a push lately, I'm not sure by who, and I've seen probably one inverse trig function included on each AP exam, maybe AB, maybe BC, for the last couple years now. So I think it's important to be comfortable with them. Now, full disclosure, most of the derivatives and antiderivatives we do today are going to be more complicated than anything you would expect to see. But they're more complicated for a couple reasons. One, it's good practice for you. Two, some of them will involve U-substitutions. And three, there is always a chance that you will need to do something this complicated. So let's get to it. There's a quick opener, A and B here, and it's a review of derivatives. So not integration, not antiderivatives. You need to take the derivative, of course, remembering the chain rule. Once you've done those, you can unpause and see how you did. All right, hopefully you did okay. The only two derivatives that I require you guys to know are the derivative of inverse sine and the derivative of inverse tangent. There are, of course, four others. Inverse cosine and inverse cotangent are almost identical to the two that are up there, and I've never seen secant or cosecant show up on the exam, so I just don't focus on it. And if they do, then you can leave some comments on here and say I need to update this video. Not a big deal, but I figure 2 is better than 6. So the derivative of inverse sine is 1 over the square root of 1 minus what was inside the inverse trig function squared. Now, everything here, and I should have done better with the colors and maybe some zoom, everything here that is in red is all the derivative of the inverse sine. But that means then that there's a derivative we haven't done yet, and that's where the chain rule comes into play. We haven't done the derivative of 2x, and that is because inverse sine is on the outside. It takes priority through the chain rule. So we, of course, need to do or multiply by the derivative of inverse sine, of 2x, which is 2, and then we can put it all together and find that our antiderivative is something like this. I am going to do 2x squared because this will become important later, especially when we go backwards. This is 2x times itself, which is, of course, 4x squared. Nothing bad. Let's do inverse tangent. And actually, before I do inverse tangent, I'm going to rewrite this. I really do prefer, I need the ddx, I really do prefer instead of x divided by 2, I really like writing it as 1/2 x. If you're more comfortable with it the other way, that is totally okay. Both are great. But we all have our different little idiosyncrasies about how we like our math written. So, derivative-wise, I'm going to do inverse tangent in red as well. And the derivative of inverse tangent is 1 over 1 plus whatever's inside squared. What was inside? Oh, that was the 1/2 x. Awesome. Except now there's a derivative that's unaccounted for, the 1/2 x, so we need to multiply by 1/2. There's a couple ways to treat this. You could keep the 1/2 there. You could also distribute the 1/2, the 2 to the denominator and the 1 to the numerator, or you could make us all cringe a little bit and you could write this as 1/2 in the numerator and then 1 plus, let's square both of these, 1/4 x squared. Whatever works best for you. There's no real correct way to do this, and you can leave any of those answers, even this guy, and get full credit on the AP exam. Great. There's our review of derivatives, but of course our focus, based on the title, are the antiderivatives of inverse trig functions. So, reverse. I think you're probably too young for that song, but that's okay. You can look it up. It's a good one. Okay. A and B here. Now we're going backwards. So I'd like you guys, again, to try this on your own. The answers are going to be inverse trig functions. And then once we've done those and gone over them, I'll give you a couple hints on further problems, and then the rest is you guys just working through, getting some practice in. Ready, set, go. All right. How did you do? Well, this first one, you might have originally been thrown off by that 3 up there. However, if you remember, 3 is a constant, and although we've stated it not formally yet, but we have said you can factor out constants from an integral, and so we can write this as 1 plus 1 over 1 plus x squared dx. And then working through, hopefully we recognize this as the derivative of inverse tangent. So the antiderivative is, of course, inverse tangent. And I apologize. I'm using the arctan notation just because, again, I like that notation more than the other. So if you wanted to write this as 3 inverse tangent of x plus c, you totally can. And I've probably gone off on my soapbox before about this, but I much prefer this notation just because I hate that little stupid exponent, right? Whenever I think an exponent, I think it should act like an exponent, but this is the one time where it's not an exponent. That does not mean 1 over tangent. That just means inverse tangent. And why are we changing rules in math all of a sudden? That is just crazy. So I much prefer the arctan notation so we don't get confusing exponents in there, but either way, whatever works best for you. Okay, this one also might be a little bit trickier. Oof. And the reason it's trickier is because of this guy in here. Now, I'm going to do this one a little bit quickly first, and it might appeal to some of you more, and then I am going to show you a different way to do it as a second try. So, the faster way first. I know, unusual, right? The faster way first is I'm going to keep the 4 up here and rewrite this. And we'll have to do this for both ways anyway, so maybe I should do this up above. So we are going to rewrite this as 1 minus a whole quantity squared, because right now 16 isn't being squared. This is 16 to the first times x squared. So if we rewrite this as 4x, that quantity squared, hopefully we understand that is the same as 16x squared, this starts to look a little bit better. In fact, slightly ignoring the 4, we'll come back to that, and pretending it's a 1, isn't this just like our inverse sign from the beginning, though inverse sign used 2x and this one's 4x? So looking at the 2x, you might say, oh, 2x is going to be inside of inverse sign. That's probably it, and so then we check it. We say, okay, is this going to be, and I guess now we can work out, we'll continue over here. Is this going to be the inverse sign of 4x plus c? And the answer is yes, it is going to be that. There, I missed the dx, sorry. It is going to be that because the derivative of inverse sign will be 1 over 1 minus what's inside squared. But then the chain rule will multiply by an extra 4, which is where that 4 on top came from, and so we're good. Now, you may say, whoa, 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 Mr. Grant. I would never have thought to do that in a million years. How did you know to rewrite this inside? And the answer, of course, is experience. And it's very hard to teach experience, right? You can, tell your friend that you should not date that person, and they are probably not going to listen to you. And they need to experience it to understand that it was a terrible idea and you're actually a good advice giver. And that may happen 3 or 4 or 100 times. But either way, you can't tell experience. You need to live it to learn it. So here we go. How do we do that? We do extra questions. Now, I did say I would give you a different way to do this, but I have an example just like that down below, so I don't think I need to take up any of your extra time. So what are you guys doing today? Well, you have about 12 questions here that are going to give you an answer to a riddle. And I'm going to give you some hints. They're all on inverse trig functions. I'm going to give you some hints on how to tackle those. And in fact, if you look at these tips carefully, you'll notice they're pretty much the same problems as the riddle. So it should take care of some of those problems for you. But I think through these 5 tips, you'll be able to get through every problem on the riddle, nothing too bad. And again, if this is like, wow, this is crazy tough for me, I'm not really getting it, that's okay as well. The main thing you need to realize are the derivative of inverse sine and the derivative of inverse tangent, and then going back through basic problems. I would consider this a basic problem, and I'd probably consider this not a basic problem. That's probably a little bit too challenging for the AP exam. But you will get some extra practice here, and it's never a bad thing to challenge yourself mathematically. You might as well practice at a higher level than what the AP exam gives you. So here we go. Tip number 1. If the numerator is a constant, factor it out. Now, there is an exception here, and that is if there's also the same value in the denominator, you may not want to factor it out, right? That was up here. We didn't factor out the 4 because we didn't have to. But you can always factor it out and still get the right answer, and you're fine. So by factoring that out, we start to fit one of our 2 main forms, right? And the 2 main forms we're looking for are either 1 over 1 plus something squared, or 1 over the square root of 1 minus something squared. Inverse tangent, inverse sine, respectively. And if we can make it fit those formats, then we're probably doing pretty well. And so over here, by factoring out the 2, we've pretty much made it fit that format, though I think we switched the order of this, but order's unimportant with multiplication. So it becomes 2 times the inverse tangent of x plus c. Cool. Tip number 2. If the denominator has a constant, factor that constant out. Now, what do I mean by a constant? In particular, I mean if the denominator doesn't have a 1 that's adding or subtracting, we need to make it a 1. And over here, I do not see a 1. I see a 4. And it has to be a 1 if it's going to be inverse sine or inverse tangent. So how do we factor that out? Well, first, we cross our fingers and hope that that is constant to both of them. In this case, it is. So we factored out the 4. Woo! Now we have a 1. But there still is this pesky 4 kind of hanging out in the square root, and we don't want that because there's no extra number hanging out in the square root. So we just start to reduce our roots, realizing that 4 is multiplying here. And when you have two things multiplying, two factors multiplying within a root, you can actually distribute or split the root like so. Realize that square root of 4 is 2, so you really have a 1/2 hanging here, so we factored out the 1/2. And hopefully you can prove to yourself if you multiply those together, you get 1. If you multiply those together, you get the same thing here, right? We're just undoing those. So I factored out that 1/2, and hey, look, now we have something that's going to be a little bit easier. We have 1/2 times the inverse sine of x plus c. Cool. Okay. Tip number 3, and this really goes back to that problem from earlier where I said I'd give you an extra way to do it. Now, this also relates back to U-substitution, which is why I think it's a very good lesson to follow the one that we just did. You must rewrite the interior of the denominator, whether it's in a square root or not, as a whole quantity squared. We saw that earlier. So we're going to rewrite this by taking the square root of 25, that's 5, and writing it as something squared. In order to fit our pattern up here, we want to make sure, if you want to make this easier, we want to make sure that we do a U-substitution here. Now, you don't have to do a U-substitution, and I will show you how to do it without a U-substitution, but the U-substitution will work every time without any guess and check. If you don't do a U-substitution, oftentimes you will have to guess and check, which may appeal to you. So how do we do it with the U-substitution? Well, I said let U equal 5x. So I'm just going to keep track of everything I'm doing here. That becomes 1 over the square root of 1 minus, and then we're replacing, let's do U in red over here, 5x with U. We're like, that's pretty cool, because we know the antiderivative of that is inverse sine. But there is still one piece we haven't accounted for, and that is, of course, the dx. We need to replace that differential with x with something that ties into the u. So let's take the differential of both sides. Differential of u is du. The differential of 5 is a constant. It stays. Differential of x is dx. So it tells us if we had a 5 dx, we could replace that with du, but we don't have a 5 dx. We just have a loner dx at the end. So we should probably divide the 5 off. 1/5 du equals dx. And now we can replace dx. We can replace it with 1/5 du. And now we're moving through. Okay, so as we go through, I'll maybe work over on this side. I'm going to factor out that 1/5 so we don't confuse anything. 1 minus u squared du. Everything's in terms of u, so let's work this through. 1/5 inverse sine of u plus c. And don't just clap your hands together and say, woohoo, we're done, because the original problem had x in it, so our answer better be in terms of x as well. But that's just one last step. We need to remember that our u substitution, we did this in red over here, was for 5x. Okay. Now, again, I did mention there would be a second way to do this, and I should probably follow through with my word this time. The second way still involves rewriting this as something, a whole quantity being squared, not having a coefficient that's not squared. Once you get there, we should recognize that this pattern is essentially inverse sine. And because the 5x is being squared, we should be able to go right to our answer and say this is the inverse sine of 5x plus c. But that's not quite right. And because we're doing this guess and check method, we should probably check our answer, right? So if I did a quick check and I said I want to take the derivative of the inverse sine of 5x, and of course you could do this in your head, maybe. The derivative is 1 over the square root of 1 minus 5x squared, but then as we saw in the opener, times an extra 5. And the original problem had no 5 in the numerator, so something had to have canceled out that 5. Oh, but what if there was an extra 1/5 hiding out front? Then it would have canceled the 5 and we'd be golden, so we need an extra 1/5 right here. Again, the U-substitution will work every time without guess and check, so some people prefer that. Others prefer just looking at that going, oh, I know it's inverse sine of 5x, and thinking about the chain rule, there's got to be a 1/5. Cool. We want to make sure we cater to multiple learning styles. Got to hit all those buzzwords. All right, 2 more tips to go. If the fraction looks like the derivative of inverse tangent, or, same idea, the derivative of inverse sine, then you definitely need to make sure you're adding 1 or doing 1 minus in the denominator. And we said this earlier too. We said this should be a 1, right? Or up here we even highlighted those need to be 1s. So this is just a separate example, but using inverse tangent this time, because this plus is not a 1. So how do we make it a 1? Well, one option is you could divide out a 9 to the out front. You could say, oh, we want to pull out a 9 like this, and then you could go from there. However, I wanted to give you a second option too, because sometimes people prefer this method. And the second option is, instead of factoring out a 9, they actually divide everything by a 9. So they went through and they said, okay, we're going to divide these by 9 to turn this into 1. But with a fraction, if you divide everything in the denominator by 9, you also better divide the numerator by 9. And then you can clean this up pretty well, right? The 9s cancel, and by cancel, of course, I mean make a 1. And we have a 1/9 at the top. And then you can factor out the 1/9, and we're pretty much home free, right? 1/9, this is inverse tangent plus c. Not bad at all. Okay. Last but not least, and we mentioned this one as well, make sure that you have a positive 1 in the denominator for inverse sine. Again, this one really also goes back to this guy, and you can actually do it the same way as this guy, but some of you might balk at the idea that there isn't a 25 in common to both of those. So you might say, oh no, I don't know how to factor out a 25. I know it's 1, but I don't know what goes here, and then I'm sad and I cry. So what we're going to do instead is the same tactic that we did up above. We're going to brute force turn 25 into 1. And we do that by dividing 25 by 25. Of course, if we divide by 25, we need to divide everything in the denominator by 25. And remembering that 25 is in a square root, we also need to divide the numerator by the square root of 25. How does this simplify down? Well, the 25's become a 1. 1 divided by the square root of 25 is 1/5. And then because we know for inverse functions everything needs to be written as a quantity squared, and 25 doesn't have a square on it, we can rewrite this as x divided by 5 squared. Maybe you can convince yourself that those two are equal. Okay. We can factor out the 1/5, and then from here you have 2 options. Okay, I'm going to again show you the U-substitution to take up most of the lower space, and then I'll show you the guess and check way over on the right. So U-substitution wise, what do I want to do? Well, I want U to replace this interior piece so it looks exactly like the derivative of inverse sine. So we're going to let U equal 1/5 x. That'll take care of that guy, but we still haven't dealt with the dx. So to deal with that, we do du. 1/5 is a constant. Differential of x is dx. If we had a 1/5 dx, we'd be in business, but we don't. Maybe multiply both sides by 5 to get rid of the 1/5. So 5 du can replace a dx, and now we're looking pretty good. So over here, we have our 1/5 that's still hanging out front like, hey guys, what are you all doing in there? How come you're showing so much work? I'm already done. And then we have 1 divided by the square root of 1 minus something squared. What thing squared? That is u. And then at the end, we said that this is going to be 5 du. Well, I'm going to move this 5 out front, but then it's going to cancel with the 1/5. So we're really just left with this. Well, that's exciting. This gives us the inverse sine of u plus c. But we should probably go one step further, and the u needs to be replaced with our original function of x, which is 1/5 x plus c. There aren't that many steps. So, I mean, this is a little bit algebraically intense, but then it's just a quick U-substitution, nothing terrible, and we're in business. I did promise you, of course, a second way to do this, and it is totally up to you which way you prefer. This way tends to be a little bit faster. And honestly, you could even go from over here if you wanted, and you could say, hey, this to me looks like inverse sine. And in particular, it looks like it's inverse sine of x divided by 5, or 1/5 x if you'd like, plus c. And then you'd say, well, am I done? And you do have to do a quick check. Maybe, again, this is mental math. And you're like, if I do the derivative of inverse sine of 1/5 x, do I get the same answer? Well, that would be 1 over the square root of 1 minus 1/5 x squared. Looks good so far. But times the derivative of the inside times an extra 1/5. And you're like, but there is an extra 1/5 there. And I'm like, oh yeah, you're totally right. Good call. This does match. And so if you tried the guess and check method, it might actually be faster. To-do list for the rest of class, you were asked to correct your final exam, so make sure those are turned in. Most of you are already done. And then the second part is the Riddle Worksheet, right? This Riddle Worksheet is on this next page, and the question is, what is happening in this calculus problem? You're like, whoa, what is with this ugly copy? No, that's on purpose. It starts off very bold, and then you can tell that like the fraction signs start to break apart, and then you're like, whoa, what is this crazy answer down here? Why is everything all weird and wonky? Well, if you solve these 12, match them to their letters, and then fill the letters in down here, you will have the answer. And it is, of course, like anything we do, hilarious because it involves math and a riddle. It's kind of a joke. There are some hints on the last page on how you could start each problem if you'd like. Totally up to you. I do think the problems get harder as you go from 1 to 12. You do want to show some work, and I will honestly admit that you probably can't fit all of your work, especially for like 9 through 12, in the boxes there, so you may want a spare piece of paper handy, or you could just work on the back. But you should probably not take a look at the hints first. You want to see what your own brain can do, and then only if you're stumped, take a look. You'll, of course, know if you did it right, if it matches an answer and the answer makes sense. Good luck, and thank you for tuning in as always. Get to work on those inverse trig functions, and I'll see you back next class for day 67.